In part 2 of my Gauss Law video series, I promised that I also talk about electric field inside the hollow sphere, but then I actually forgot to do that. So before we move on to the next example, I just want to discuss the case of the electric field inside a hollow sphere where all the charge on the surface of the sphere. So here's the picture, the same ball as before, radius big R. But now we're interested in the electric field inside, say a distance little r from the center. Now, the symmetries are all exactly the same, right? It's always still spherical and so on. So steps 1, 2, and 3 work exactly as before. We just have picked a smaller Gaussian surface that is now on the interior of the charged sphere. Right, remember, we can pick our Gaussian surface any way we want. That's our choice. It's like a mathematical object. It's not physically there. What's physically there is the charged sphere. So steps 1, 2, and 3, they were all the same. We figure out electric field must be radial because going in any other direction would violate the symmetry of the setup. And so we figure out, okay, we're going to pick the surface that's the right surface to pick, and so on. Now, step 4 is where we're meant to discuss, we're meant to find the charge inside our Gaussian surface. Well, what is the charge inside this surface? Remember, all the charge is on the surface of the sphere. If you try to visualize it in 3D, right, it's kind of a smaller imagined ball inside the bigger ball. Well, what's inside the smaller ball? It's just empty space. So, Q inside is not the Q, the thing we call the total charge of the sphere, but it's 0. Okay? Because all the charge is outside of this. It's surrounding it, but none of the actual charge is inside our imagined sphere. As long as little r is smaller than big R. It's the case we're considering. So that means step 5, right, we get Gauss's law. Gauss's law says electric field, radius r times 4 pi r squared. This comes from steps 1, 2, and 3 just as before. Hasn't changed just because the r is now smaller than the radius of the charged sphere. It's equal to 0 divided by epsilon naught. Of course, that's just, 0. Well, r isn't 0. 4 pi isn't 0. Epsilon naught is not infinity. Right? So what it implies is that the electric field strength inside the sphere is 0. Okay. So, is it something you could have known without Gauss's law? Well, good question. So, say we didn't know about Gauss's law. I could imagine this sort of this sphere here, this shell, right? All the charge on the surface, and think I say, okay, the electric field outside is probably going to go like this, assuming Q is positive. If not, oops, it's just in the reverse direction. But inside, you might sort of guess, maybe it's like, maybe, what might the electric field look like? Maybe it's sort of inwards, maybe? And then you're like, okay, but that, right, you run into trouble with how can I connect up those field lines? So you can sort of guess, I think, plausibly guess, just from understanding field lines and the rules that they have to obey, that the field inside here has to be 0. But it's all a bit fuzzy, right? Gauss's law. Super easy. Electric field inside it is 0 anyway. There's no electric field inside. No E field inside. Now, could you have calculated that In principle, yes, right? You could have taken a point here, and you could have figured out what's the electric field due to this chunk, due to this chunk, due to this chunk, due to this chunk, due to this chunk. In 3D, all around, you can do this. And you figure out that these bits down here would create electric field like this way, this way, this way, whereas the electric field, the charges over here would create an electric field the other way. There's more over here on this side. There's more on this side than on this side, just because this thing isn't in the center. But those bits are further away, so they're weaker each. Are they going to add up to exactly cancel out the electric field from these ones? Maybe. Not an easy calculation to do. Ultimately, you find yes, it does. You find that no matter where you pick your point, if you actually work out this complicated integral of the electric field contribution from each little chunk of the sphere, it's gonna work out that all those fields pointing like this way, like downwards, but from those bits up here, they get cancelled by the field bits pointing upwards from these bits down here. And the whole thing in 3D. Like from, sort of coming out of the page as well. Not an easy calculation. Something you might sort of guess from the field lines. But Gauss's law, it just gives it to you. Right there. Okay. So that was just finishing up with that example. Inside and outside the hollow sphere. So now let's go to example 2, and I took the liberty of pre-drawing 2. Example 2 is an infinite charged rod. So imagine if a charged rod, much like this pencil, right? And it's infinitely long, which I can't really draw. In practice, we don't have infinitely long rods, but you might have rods that are very, very long, or cables, say, that are very long. And as long as we're staying fairly close to the cable, from a like vantage point here, the cable looks to be effectively infinitely long. To a good approximation, it's infinitely long. So we want to know the electric field, let's say over here, that this is a distance r from the rod. Now this is the example for which I actually have written a whole long multi-page worksheet that guides you through the calculation. And I'm going to put up a link to the worksheet underneath the link to this video. So you'll be able to work it through yourself with all the hints of how to apply Gauss's law and so on. But I'm also going to do it right here. Okay, so we want the electric field there. Write this out. Want the electric field here. Okay, let's think about the symmetry first, right? This is step 1. Step 1 of applying Gauss's law. What is the symmetry here? Now, this thing is not a sphere, right? If I rotate this, say, this way, it doesn't look the same anymore, right? It has changed. So what can I do to this, this charge distribution that does not change the setup? The one thing I can do is I can rotate it, like this. In our case, we imagine this to be infinitely thin, but the same would be true if I had, say, a sort of pipe that's not infinitely small in radius. That's another example you can work through. In our case, we imagine it's an infinitely thin rod, or the charge along one narrow line. I can rotate it like this. That doesn't change anything about where the charges are. The other thing I can do is I can move it up and down like this, and because it's infinitely long, this doesn't change where the charges are, right? You can't tell if you come in the room late whether I've moved the rod to here or not because it's infinitely long. Because a finitely long pencil, different story. And the other thing I can do is I can take it and say, oops, flip it. Right, infinitely long rod, flip, looks the same. Charge density, the linear charge density, is assumed to be constant. It's not the case, again, different story. But we assume any chunk, any centimeter on our wire has the same amount of charge in it. So what's the symmetry here? The symmetry is a cylindrical symmetry. Right, a cylinder is something you can rotate. So here's a cylinder, right? Now imagine without this metal piece, I can just rotate it like this. It doesn't change anything. If there's no metal piece, I can move it up and down. And I can flip it. None of those things change anything. So I'm going to pick a cylinder for my Gaussian surface. So let's write this down. Cylindrical. Symmetry. We pick cylinder. Now we want the cylinder to go through our point, right? The surface of the cylinder has to go through our point here, so we are going to pick a cylinder of radius r, where the radius is the distance where we want to find electric field. So let me try to draw this, and I'm going to do what I can here to do it in 3D. So it might look something like this. Side here is sort of hidden, right? Should be sort of behind it. Something like this is the best I can do, right? The charged rod is going to be right in the middle. How long should our cylinder be? Well, should it be infinitely long? Let's think about this. If you make it infinitely long, we're going to have an infinite amount of charge inside it. And the flux through it is going to be infinite because electric field is sticking out in all directions. So our Gauss's law is going to say infinity equals infinity. Well, that's no good. That doesn't allow us to solve for anything. Well, infinity equals infinity. Infinity times 2 equals infinity. It's just that we can't do math with that. So let's pick a cylinder of length L. It's called L. Now, remember, L is something we choose. Like, we imagine the cylinder. It's not actually there. It's something, a mathematical object we get to pick. So, whatever our final answer is, it better not depend on L, right? Let's see if that works out. We pick a cylinder of radius R, length L, where L is arbitrary. R is not arbitrary. The radius is not arbitrary. The radius is, somebody says, find electric field 5 centimeters from here. They're like, okay, make R 5 centimeters. Okay, so what does the electric field look like? Again, let's assume this is a positively charged rod. If it's not, just the field lines will be backwards. The field lines, they have to stick out radially from this rod. Why? They can't be at an angle like this. If they were at an angle like this, then if I flip the rod, I'd flip the way the electric field looks without changing anything about the charge distribution. So again, it comes back to symmetry. You're on step 2. Right? I can't have an electric field that's not radially outwards. Because if there was such a thing, if there was a component of electric field that, say, points this way, then after flipping my setup, it points the other way, even though my setup hasn't changed at all because of the symmetry, right? So that reasoning tells me that the electric field must be sticking radially outwards. This is hard to draw in 3D. I can draw it, over here and down here. I'm not going to attempt to draw it sort of coming out in all directions. It's just going to look messy. I won't be able to, to give you a picture that makes any sense. But you could imagine it's sort of like a long rod with spikes sticking out of it in all directions. That's the electric field. Just from the symmetry, haven't applied Gauss's law or anything. I've just thought about the symmetry of my setup. Could be pointing inwards, right? But we already kind of can guess, okay, the electric field should be pointing away from positive charges. Okay. So this was essentially step 1 and, well, not step 2 yet. We haven't argued that the electric field is constant, but it has to be, right? E field is radial, and the strength is constant on the surface of the cylinder. Now you might ask, what about those sort of ends, like the lids? I want to come to those. So by surface of the cylinder, I mean the round surface of the cylinder. It's constant because suppose it wasn't, right? Suppose, argue by contradiction, suppose the electric field here was stronger than the electric field here. Same distance away, just the other side of my cylinder. Well, then I could imagine I take my charge density and I just rotate it like this. Electric field would rotate with it. Well, now the strong one here is down here and the weak one is up here. So I've changed the way the electric field looks without actually changing anything about my setup. So it would be a contradiction, right? The electric field shape would contradict the symmetry of the setup. Okay, so the electric field is radial and the strength is constant on the surface of the cylinder. So what about the angle? Well, because it's sticking out, right? Let's take a little piece of area. Let's say this bit here. Right here, right at the top, the flag sticks out like this. Again, the way the little flag is defined, right? It sticks out perpendicular to the surface itself. That's how the direction of area is defined. Again, go back to part 1 if you don't remember that. So the angle between the electric field and the flag is once again 0. So E dot dA is just equal to E, the field strength, times the size of the area element, never mind the direction, times cosine theta. But the angle cosine theta is the angle between the flag and the electric field, and that is just 1. Because the angle is 0. Yeah, 1. And the electric field is constant. So once again I've shown that the flux is constant from one little square to another. So the flux through this thing is the same as the flux through this thing, as long as it's the same size, equal to the flux through this thing, equal to the flux, I try not to draw sort of here, but you could imagine that if I pick this part of the surface that's on top, that's also the same, like sticking out of the page. As I say, hard to draw in 3D. Hopefully you can visualize it. Okay, so the flux is constant. Across the surface. You could say the flux density. I'm going to say the flux constant across surface. And let's work out what it is. This is, I guess, step 3. E dot dA. Our surface S is the green one. It's gonna, you know what it is, right? Haven't actually labeled it. The cylinder is S. That is going to be equal to, well, the cosine is just 1. The electric field is constant, so it goes out front, the electric field strength. Again, it's a function of R, so I probably should have put this in here as well. Times summing up over S all the little bits of area. Right, I've used this is 1, it goes away, and I can take this because it's constant, because all parts of the surface are the same radius. By my choice of symmetry, I can take this out the front of the integral. Then this is just going to be the surface area of the round part of the cylinder. Now, a round part of a cylinder, you can visualize this. You take a sheet of paper and you roll it up like this. Right, here you go. But because it's just a sheet of paper rolled up, the surface is just the surface of the sheet of paper, which means it's the circumference. So I can imagine I sort of cut the paper here, and then I've got a sheet of paper where the one side is just the circumference, the other side is the length. So this is just equal to ER, can't see this, ER times the area of a cylinder, which is 2 pi r, the circumference, times the length L. Okay. The part that I haven't talked about yet is the ends, right? The end pieces, those little circles, they have to be included. If they're not included, it's not a closed surface, right? If you imagine filling the cylinder with water, well, I need to have those end pieces closed. But what about those end pieces? Let's write this down. What about the end pieces? Well, let me just draw one of those end pieces. So here's my end piece. Right, the cylinder goes sort of off like this, and there's the charged rod inside it, and that sort of goes off like this. Right, and just care about the surface on the front. Well, if I look at the electric field, we know the electric field is radially outwards, like this, like this. Okay, this is hard to draw in 3D. Right, it's sort of radially outwards. But the flag, say this point here, the flag sticks out like this. Right, it sticks out perpendicular to the surface, while the field lines are in this case parallel to the surface. So E on the lid, I'm going to call it the lid, you already know what I mean, like the top and bottom, is parallel to the surface. There by surface, I'm only talking about this round circle, right? It closes the end of the cylinder. Whereas the dA, the little area where the direction is the flag, is perpendicular to surface. So what does that mean? Let's figure out the flux of a little chunk of area here. What's the flux through that bit? Well, the flux through some tiny chunk dA is equal to E dot dA is equal to the field strength, whatever that is, probably not 0, it's something, times dA times the cosine of the angle. The angle in this case between this one and this one is going to be 90 degrees, because they're perpendicular to each other, but the cosine of 90 is 0, so there is no flux through the end pieces. No flux through end pieces. Of course, I've really spelled it out in detail here. Once you had a bit of practice, you just look at it and you're like, okay, E field perpendicular to the flag, 0, right? But it doesn't contribute to the flux. Okay, so now we can write down what the left-hand side of Gauss's law is. We've completed steps 1, 2, and 3. We have that E dot dA is equal to E, strength of the E field, times 2 pi RL. Apart from the round, right, the round surface, the cylindrical surface, the end pieces. Right, normally I'd have to say plus flux due to end pieces, but that is just 0, so that is the final answer. Now comes step 4. Now we want to find the charge inside. Find the charge inside. Well, let's have a look at our picture. So the ends are closed, so there is definitely some charge inside, right? There's the piece of the rod that is sort of trapped inside. Like the rod passes through the surface, because the surface is the mathematical object, right? But he sort of cut it off. The length of rod inside the surface is just L. So let's write this down. But say this is 2 meters, just as an example. You know, we can pick 2 meters. Why not? Let's pick 2 meters. Then what's the charge inside it? Well, we're given a certain linear charge density that says there are 3 coulombs per meter. If there are 3 coulombs per meter and I have 2 meters, then I have got 2 times 3 coulombs, makes 6 coulombs inside. So the total charge inside, well, Q inside, it's going to be the length of the rod times how much charge do you have per length. Right, this is in 2 meters times 3 coulombs per meter. Makes 6 coulombs inside. Okay, done. Now, let's go to step 5. Write down actual Gauss's law, rearrange it. So we have on the left-hand side of Gauss's law, we have like this is the left-hand side, so we've got this expression here. E is a function of radius. The field strength, I know the direction already. It's radially outwards, times 2 pi r times L. That better be equal to Q inside over epsilon naught. It's going to be L times lambda divided by epsilon naught. Okay, thank goodness, right, the L's are going to cancel out. Remember, that has to happen because we made up the cylinder. We picked our length L. And the electric field strength better not depend on some kind of mathematical choice we make of our imagined surface. Those are going to cancel out. So we're going to get, everything said and done, lambda divided by 2 pi epsilon naught times r. So what does it tell me? It tells me the electric field becomes weaker as 1 over r as I get away from the rod. For getting away from a sphere or point, it was 1 over r squared. So it becomes weaker faster if you get away from a point than as you move away from a long rod. It only falls off as 1 over r. It's an inverse law rather than an inverse square law in this case. Is there an inside of our charged rod like thing, like there was the inside of the hollow sphere? In this case there's not, but if you imagine you had a pipe instead, like a charged pipe, then there would be an inside, and I leave it to you to figure out what the answer is then. But this is our solution to the charged rod, and you can double check that this matches what you worked out with integration last week. Okay, again, this video is already about half an hour long, so I'm just going to split all the individual examples into separate videos. And this was example 2, the long charged rod. In the next one, I'm going to start with the sheet of charge density eta.